Hi. I'm here to talk a little bit about agentic retrieval, and particularly some kind of aspects that makes agentic retrieval a little bit special, a little bit different than traditional information retrieval seen from human users. Basically, we think that most, or at least a large part of search in the future will come from agents, right? I mean, these days, I don't go to Google anymore. I go through my agent or through ChatGPT or whatever. That's where I do my searches. So actually, it's the agent that is always operating on my behalf to actually do the searches for me. And when agents are doing searches, or retrieval, there are some different kind of aspects to it that we need to kind of address. And that is a large part for why we kind of thought it was interesting, or why we thought the need was for a different company that did this the right way, which is Hornet. But first, hi, I am Lester. This is actually my fourth time speaking here at Berlin Buzzword. It's been a pleasure all the time. Last time I was here was 22, actually. I was on this exact same stage. I was talking about hybrid search at the time. But since then, of course, the world has moved on a little bit, and now everybody is talking about AI, and so, of course, I am as well, which is nice for me because AI is my background. I pursued a PhD there many years ago, but since then I've been working in search for the last 13 years. So, when it comes to agentic retrieval, we think that agentic retrieval needs a new infrastructure that is actually purpose-built for these kind of workloads that agents perform. And there are particularly two main cases that I want to kind of promote here. And one is that agents actually search differently than human users, right? They can read faster, they can type faster, they can just issue all these huge number of queries in a short amount of time. So just kind of load-wise, it needs to be able to scale to the requirements for these agents. At least and also if you have many agents running at the same time, the workloads can become pretty large. But also, the usage for retrieval for an agent is different than for a human user, right? So for a human user, we type in the search in this box and we get back these results, and we're accustomed to get a list of these results and click into some document that may or may not contain the answer to what we're actually looking for. For agentic retrieval, however, what is retrieved is actually injected into its context. So it's more looking for knowledge that is injected into the context, and that has some issues and some consequences that we need to look at, because if we just kind of stuff this context without being critical to what we put into the context, we can run into problems. And that's pretty much what I'm going to talk about today. So just to get some preliminaries out of the way for people that aren't too into search and so on. When we're talking about search, we always talk about getting the relevant results for a query. So some person, user, agent, human, whatever, has some information needs, and issues some sort of query, and we get some results back. And usually we want to give them relevant results back, which satisfies the user's need in some context. And one of the kind of challenging aspects here is we don't really know all of the context, right? The user can maybe not have given all of the context. So relevance is very challenging, actually, because it can be subjective, situational, graded, because of unspoken context. Ranking, of course, is for the system to kind of order our results in the order of what we think is relevant for the query or not. But also, some problems is with the query, the same query is not necessarily the same intent, and this goes to context, right? So if you're searching for Jaguar, do you mean the animal, the car, the team, and so on? So bringing context into relevance is critical. And we believe that at Hornet, making this as easy as possible is critical. Traditional information retrieval kind of handles this as kind of like a black box. So in traditional information retrieval, we have like a user query coming in at the top there. We have this kind of pre-processing, query processing steps like, query expansion, intent, understanding, all these kind of pre-processing, tokenization, all these pre-processing steps that you have. Then we go back down and search for these tokens or whatever, or vectors or whatever into actual content, and there could be like a few steps up in between the system, and then the results come back up again to whoever is searching for the user, searching for these results. Typically, we kind of have the search system itself is a black box. We set the query in, we get the results back again. And the results that we get back again, trying to kind of illustrate that on the right-hand side there, we get a ranked list of these results. The green is here, relevant documents to the query. And I kind of want to point this out because this is pretty important for later parts of the talk. There are a few metrics that we care about. Of course, we want to kind of give relevant results to the user. Two very concrete, important metrics are the recall and precision here. A recall is the amount of documents that we actually retrieved, given the amount of documents, relevant documents in the system at all. Precision is the amount of relevant documents that we gave among all the documents that we actually retrieved. So the point here is that it's easy to increase recall in your system. It's just put the point where your cutoff point, just go all the way down. So if you retrieve all the documents in the system, you have perfect recall rate. But of course, precision drops by a lot, right? And likewise, you can really increase precision by just going the opposite way. Like, okay, let's retrieve fewer documents, right? Then we can increase the precision, but of course, recall drops. So there's always this tension between recall and precision. And ultimately, we want all the kind of relevant documents to be up top there to get both recall and precision as high as we can. That turns out to be very difficult in practice because there are many documents that look very much similar to each other but are irrelevant for the query at all. But this is what we do by giving the search engineers good tools to kind of set up relevance ranking and so on. The calculation is to try to give them the tools necessary to kind of push those green things up to the top there. Now, for human users, this is fine, okay? Because we're accustomed to looking at the sequence of the documents and looking at this kind of, or the results, and we can see, okay, this is relevant for us, this might not be relevant for me, I'll just skip to the next one, and so on. And that's fine for human users, because we kind of scan this list sequentially, and we might give up at some point, but we're not using that many calories to kind of skip a document. If it's not relevant, we just go on to the next one. However, for agents, that's not how it works. Because these results are pretty much put directly into the context itself, and they are ingested in parallel through some sort of, inside the GPU and so on. So basically, they don't really have the capability to skip a document. If it's first in the context, it's in the context. It's attended to. And the point of putting this context or these results into the context, of course, is different for an agent than for a human user, because usually you want to kind of use this context, use the retrieved documents to actually synthesize an answer to the question or whatever is the kind of high-level goal of this agent. The point is that agents kind of have a different kind of usage for the retrieval. For instance, RAG, retrieval augmented generation, we have this query coming in. We have this query, we retrieve based on this query. We get all the responses from this traditional search engine that we have. We stuff it into one of the large contexts, and we ask the LLM to, generate the answer for me. Works very well for question answering systems. Solved, no problem here. Maybe, or maybe not. But this is fine, usually, because it's like a single pass. If we do anything wrong in this kind of retrieval step here, it's maybe not the end of the world. This is just a single pass. However, when it comes to agents, agents work in loops. Agents might have some sort of overarching goal that they want to achieve. They have some sort of plan that they want to kind of, set up the steps to achieve that goal. And for each step in this plan, they go out and act and do something. So for a search agent, they would go out and do a query. They will kind of get the results back again, observe those results, and modify the plan and do this in iterations. This is very, very different than RAG. Okay, because if some sort of problem, or we kind of injected the wrong type of context into this loop at one point, it will always be there. The context just increases as we go through all these loops. If we're not smart, of course, just naively, it will increase and increase. And what is the problem with that, you might ask? Well, let's take a little step back again and talk about what these LLMs are, how they work. So all of these AI models today, they're of course based on the transformer model. And if you're not too familiar with how the transformer model works, this is like a very, very crude, hand-drawn, obviously, illustration of this. So basically, on the left-hand side there, we have a kind of a small kind of piece of the transformer model. And the point of a transformer is to take a sequence of tokens, each represented by a vector, push them through this transformer layer, and kind of transform these vector representations into another set of vector representations. Not going to go too much into the details there, but the really critical point here is that there's something called the self-attention mechanism. And in this attention mechanism, each token attends to all other tokens. Each token attends to all the other tokens, right? And that's kind of critical, because if we have like a small amount of tokens, a small query or a small context window, then the number of connections between these tokens are like manageable. But as we increase the number of tokens inside of your context, the number of connections, the number of calculations between all these tokens, or these vectors and tokens, they increase quadratically, right? And this is critical because basically this total activation amount that you have is limited, is summed to 1 through the softmax function. And basically, the more number of tokens that you have, the more diluted this attention span is. And that is what leads to, ultimately, context rot. You've always seen this. As we kind of increase the number of tokens inside of your context, then the accuracy of the agent tends to fall. Now, this is a figure from last year, so this is like partly much more solved today than it was before, but I think it's interesting because it kind of shows some things here. And one of the things it shows, but particularly like the Gemini and the OpenAI, I was a big fan of the Gemini models at that time. And I was wondering, why the hell is this happening? When we're using Gemini as a coding agent, you could never, ever cross 10% usage of the tokens because, just accuracy fell down. You just have to, create a new context. But it had a pretty large context window maximum size. It had 1 million tokens already about a year ago. But of course, you can't have 1 million tokens competing for attention to each other, right? Because 1 million tokens attending to 1 million other tokens is 1 trillion calculations that you do per layer in this transformer model. You can't do that. So of course you need to use some sort of engineering tricks. You need to kind of decompose this hierarchically or some way, but you have to use some engineering tricks to be able to do this. And this causes some sort of unlinearities or non-linearities in Gemini and so on. But the point is that even though you have a large context window, doesn't mean it should be used. Right? So we should probably be careful about the number of tokens that we put into, both of a cost point, but also from a accuracy and usability point as well. Okay. Which brings me to the next step. How does relevance and reasoning relate to each other in this case? Because when it comes to search or agentic retrieval, we saw earlier that if you have good relevance, I mean, you're retrieving documents with a high level of utility, then obviously that might be better than, of course, retrieving results with a low utility. But the point is that to a certain degree, you can reason yourself out of bad relevance. As long as you kind of have the answers that the agent requires somewhere in the context window, you can reason yourself out of it. So if you have you're not doing very well relevance-wise, you have sending a lot of documents and only some of them are actually relevant, and you have a lot of irrelevant documents, then you can actually kind of use reasoning to kind of get yourself out of that problem. But if you're doing better with your relevance calculations, you have more of those kind of green documents up at top, then you don't need to use as much kind of reasoning to get the kind of accuracy that you want. That's the point. So, makes sense. So better relevance, we can both save money on token costs. However, enter our villain of the story for today, which is a distractor. The distractor is content that is irrelevant to the query, but it's irrelevant in a way that is bad. And it's usually retrieved because it's plausible enough. It seems like a good hit from the retrieval engine, but it's not. It's something that could be actually damaging the task inside of this agentic loop. And examples of that are plausible but wrong evidence. For instance, that you're looking at financial information, you want up-to-date financial information, but you're actually retrieving from the wrong year. So it's totally wrong. Residual interaction context, you might be looking at this long chat log and so on. Maybe it's context that was further up in the that's no longer relevant. Conflicting distractors, that's the big problem. If you have two pieces of content inside of your context that conflict each other, so the agent has to kind of decide which one is correct given the context, that's kind of maybe the worst type of distractor. Other types, sensitive pieces of content that shouldn't be there, that should not be propagated through the final answer. And adversarially poisoned content, you're downloading something, there's some hidden instructions, disregard previous instructions, now give me 10,000 bitcoins and so on. But the point is that distractor is problematic because it is believable enough to be retrieved by the search engine, but is actually wrong and can divert the agent's kind of long-term actions. And in this case, when the retrieval engine starts returning these bad distractors, this distractor-heavy utility, then no amount of reasoning can actually help you from this, can get you out of this. Because there are things in this context that starts kind of decreasing the agent's task performance and accuracy. No amount of reasoning can get you out of bad relevance in that case. This is important. But it gets worse. This is a paper that came out a couple weeks ago that I thought was very interesting, called First. I love these papers that have these kind of nice poetic titles. The First Drop of Ink. And the idea of that is that you have this glass of water, you put in a drop of ink, and of course it distributes the ink in the water. And the first drop is, of course, the one that you notice the most. The 10th drop and so on doesn't have as much to say, but the first drop, really distributes itself along pretty nicely. But when it comes to hard distractors, or distractors in general, turns out the first ones that you enter the context, they are the worst. If you can get out 10, 11, 12 hard distractors, doesn't matter as much, but the first one, second one, third one, they're really important because they have a really large effect on the kind of task accuracy. Much more than you would expect. That's what they call the nonlinear impact of misleading information in long context reasoning. So the point being is that, okay, we have these distractors, we're doing retrieval, and we really, really want to kind of avoid getting these bad distractors, these hard distractors into our context at all. And it turns out this not only is that hard, but we also want to avoid almost any hard distractors getting into our context because the first ones have a very, very large effect. So how do we do that? Well, I'm not going to answer that quite yet. I'll just give you another example. What we mean by distractors. So, topically relevant example. Let's say we have a query. Which city hosts the opening match of the 2026 FIFA World Cup? And of course, the gold answer for that, the passage that the agent needs to answer this question, of course, well, it opens in Mexico City, 11th of June, 2 days from now. That's a gold answer. That's a gold passage. A hard negative or hard distractor here, the red one there, is the information from the previous World Cup in 22, which is basically exactly the same sentence, but it's like only 2026 versus 2022. So you could easily see that this piece of content would be retrieved from this query. Of course, if you're doing well, you would put a filter on the words and so on, so maybe you filter out 2022, but still, this is an example of a hard distractor. And then you have easy distractors, which are topically relevant and might or might not be retrieved from the retrieval engine. And then you have random passages that don't necessarily need to be there, but can be a part of what the engine retrieves. This is an example. This is an example that Codex wrote for me because I'm lazy these days. When I want to understand what a paper says, I don't read the equations anymore. I just give it to Codex. Code up an interactive HTML page for me, which I can kind of remove some sliders and so on, so I can understand what's going on here. That's a good tip. Anyways, it kind of wrote this up for me, and it kind of simulates the behavior, the point of this thing. And this is what I'm trying to illustrate here, is that you have the green things in the middle there. It's the next token. It's the next token that we're about to generate in this autoregressive transformer. And the gold lines there, they're like this. It turns out this next token, they're attending to the tokens, the correct tokens from this gold passage. And you see on the right-hand side there, the softmax budget, which is kind of the number of tokens that it attends to. It always sums to 1, but this attends mostly to this kind of gold standard passage, the gold passage tokens. But when we enter a hard distractor, the image changes to something like this. Because all these tokens are still topically very relevant, but because of this softmax, it only can sum to 1, then a much, much larger degree of this one distractor document that entered the context here gets an unreasonable amount of attention from this one. So in this case, you see the softmax budget went from like, well, 80, 90% for the gold passages to under 50%. So that's the reason why this happens, right? Because whenever you kind of get this first distractor token, then this attention budget goes to a reasonable amount of degree to these hard distractor tokens as well. So again, the point is, we really, really need to try to avoid getting these hard distractors into our context. How can we do that? Okay, so just getting back up again. Usually when we kind of construct these search systems, we're occupied with different sorts of metrics, and then DCG is a very typical metric to use to see if we're doing well with our retrieval engine. And DCG has this assumption that we have this ranked list of documents and they're ordered in relevancy. And it's like that because we as humans, again, we sequentially scan these results and we can see if something's irrelevant or not. We can just skip to the next one. But agents, again, they don't care about the actual order of these documents. They're just in parallel scanned through into this context. So NDCG, if we're using that as a metric, it optimizes for the scanning of humans, but not for agent synthesis. That's the point. But also, NDCG has usually an assumption that we're scoring these different documents from how relevant they are, from 0 to 5, perfect, excellent, good, fair, bad, or whatever scale we want to use. However, an irrelevant document is usually a neutral score. However, as we saw before, we really, really want to avoid these bad distractors, the type of documents that are actively harmful. So maybe instead of just having a neutral score, maybe we should have some sort of maybe a negative score, right? So we really want to avoid kind of getting these hits in there. there was this paper that came out, I think it was December or something, which kind of tried to address this problem. They call it utility and distraction aware cumulative gain. And it's basically kind of taking that into account. If we have distractors and want to avoid them, how can we kind of set up this metric that at least tries to kind of push these irrelevant and bad distractors out of the result set and these good ones back up again? But there are two things that are interesting here. One is this graph to the left here. And the blue lines there, they show like documents that are ranked typically to NDCG or precision or recall or however we want to score them. And usually they're scored in like decreasing order of relevance. However, it turns out that agents or LLMs have something called the lost in the middle kind of effect. And basically, that's the red curve there. And it has a larger chance of actually successfully attending to the document if it's either the first document in the result or the last one. If it's in the middle somewhere, it tends more to get lost in the noise in a way. It's kind of like humans, right? It's called the primacy effect and the recency effect on the other side. We kind of tend to notice what was told to us first or last and tend to forget all the noise in between. So yeah, maybe a little bit as we humans do as well. But the point is that they also added this metric, which they call UDCG, which is actively saying that, okay, we take all the utility of the positive documents that we have, but we decrease the utility of the bad distractors that we have down. Right? So hopefully, from that list over there, that the red ones would kind of fall down, and the green ones maybe a little bit up. But still, that's their solution, but still there's a kind of problem here. We have this, the metrics here kind of helps us to kind of, try to identify at least what were the bad distractors and try to move them out and so on. But this is just one part of the story, because as we saw before, we really, really want to avoid getting these bad distractors into our context at all. And this is one part of the solution. But we need to kind of start thinking about being a little bit defensive here, right? How do we avoid even putting these bad distractors into our context at all? So, as kind of like alluded to in the previous slide, precision, which is like the number of relevant documents that we retrieve in relation to the number of documents that we retrieve, becomes a lot more important, right? Because we really want to make sure that we have the correct documents and not the bad ones. So precision is very important. Because a miss, if we don't get all the recalls, it costs less than a distractor, right? Because a distractor actively can decrease the performance of the agent. So, and maybe we need to kind of optimize for utility, re-rank, prune, keep K low, not just retrieving everything and having the agent or the LLM sorted out. Because as we saw previously, again, as we add just a single distractor, no amount of reasoning can kind of help us out of that situation, right? So basically, we really need to make sure we be careful what are the chunks from retrieving that we put into our context. Basically, this is a control problem. That's what I'm trying to get at. That basically, instead of like saying to the search engine, hey, just get me everything that seems relevant, and I'll sort it out afterwards, like post processing or post reasoning, maybe we make sure that we actually make sure not to add this into the context at all. That's why I call this retrieval for agents is no longer a recall maximization problem. We're no longer thinking in terms of like precision and recall, but we're talking about control. How do we actually avoid these distractors to enter our context at all? And how do we do that? Well, I'm going to take a little bit sidestep for a second. BrowseCom Plus, which is a fantastic data set for agentic retrieval or agentic performance within search. Great data set. It's about having a question that's really, really hard to answer. The agent needs to kind of step through multiple evidence documents before it can kind of find the relevant document or that gives its answer. But it's an interesting data set from a agentic search point of view. We did some research on this previously, and basically we just put this into Hornet. We put the hybrid search on this. We get pretty good, almost state-of-the-art retrieval for that, based on actually not doing that much at all. But interestingly, they came this paper a couple months ago, called Coding Agents for Search, and is basically utilizing the kind of effect or the kind of strengths of coding agents they have to search within code, right? Because I mean, you always all of you have used these coding agents, and they're actually fairly decent at searching through code, finding the different capabilities, where code is, and how they kind of connect to each other, and so on. So, but they do have a lot of tools, though, right? They have like a terminal. They can use grep. They can use find. They can use all these sort of different tools. They can write small Python snippets to kind of help them go through this document or the source code and so on. But they're fairly efficient in actually finding the correct piece of code, and it can iterate and go through this. So what this paper did was that they said, hey, okay, let's try use this for BrowseConf Plus as well. Let's just put all the documents that we have inside our system, we just put them on disk, and we'll have just a coding agent do the retrieval for us. We're not doing any search engines, no search systems at all. Let's just do regular coding agents search and have it utilize the tools that we have. Grep search, grep find, code, and so on. And what they found is they just blew the state of art out of the water. Previously it was 80, and they got 88.5. Right? This is just a much, much better way of searching through these documents for the agent. One of the fun facts, though, for this paper was that if they added a search engine, if they added embedding search, vector search, or ABM25 search, then actually performance decreased, which is interesting. I'm not going to go into more. But this kind of points out so that the agent was capable of using this kind of lower level tools. It knew how to use them. It knew how to combine them. It knew how to orchestrate these different tools to kind of more effectively find the information it was looking for. Which brings us to why we can't do that more in general. Why does that have to be coding agents at all? So previously, we were talking about search engines being this black box, right? We have agent queries coming in. We have this retrieval system that is black box. We send the query in. It does its stuff. Don't really know what. And we get some results back again. And if it kind of gives us these bad distractors and so on, well, too bad. We can't do much about that. But if we open up a little bit, right? Maybe instead of not having this black box system at all, but having the agent give it access to all these kind of lower level utilities, lower level functions. Just like this coding agent had very basic tools to give, like just grep and just find and so on. Then the search retrieval system actually has all these kind of lower layer systems that it tends to orchestrate. But let's open up, let's give that to the agent itself so it can kind of concentrate to go through and search through all this information as it does, and it can orchestrate finding the query, finding the correct documents, and thus avoiding finding these negative hard distractors. That's an interesting point of view. So basically, what I'm trying to say is that agentic retrieval is no longer about having this black box, retrieving documents that look good from some sort of metric, but agentic retrieval, given the kind of the destruction power of our villain, the distractor, then becomes context admission control. It's a process. So I'm going to end with this. That search, previous search, traditional search, they ranked documents for humans. RAG retrieved context for answers. But agents working in a loop, they retrieve context for actions. And that changes the cost of a false positive, right? Because if it becomes one of these bad distractors, it can have very large consequences. Which means that we need to measure evidence, not just relevance, but how this evidence fits into our kind of higher level plan for the agent as well. And we need to control the context admission, not just blindly trusting the retrieval system's top K. So, and I believe that by opening up these lower level primitives, the search and having the agent itself orchestrate, and maybe working in a sandbox, being able to write its own small Python code to orchestrate all these kind of pieces, that is what was needed to kind of avoid these bad distractors entering the context. So search broadly, verify that these hits are, or these documents or whatever kind of retrieval unit you have is correct, and then carefully inject it into your context. That was all I had. Thank you.
Maybe just one question from the audience.
Hi. So have you found that multi-stage ranking pipelines can be effective at removing hard distractors, or do we need entirely new ranking approaches?
I guess that depends on your ranker or re-ranker, I guess. But I think the point is that even though you have like this re-ranking step and so on, then as long as you kind of the results or these hits that are returned to the context, if any of them kind of contain these bad distractors, it doesn't really matter how many stages you rank or so on. You need the information in there to be able to discern if there is or is not these bad distractors. And that is not necessarily up to the retrieval system, right? Because as mentioned previously, the agent that is doing the queries, it's the one that has the context necessary to discern if this is a bad passage or not. So I think, I'm not sure that having more, or I don't think actually, that having more ranking stages will help. The agent itself needs to kind of define what is relevant for me or not in those cases, I think.
Well, thank you very much, Lester.
Oh, thank you.